here. I represent the organizing committee. My name is and I hope much of you saw me at the last with Party Symposium. The last year Party Symposium took place in Ventspils. We remember the smooth organization, numerous participants, and interesting presentations of that symposium. I trust the strong ties formed last year in Ventspils have contributed to joint research activities and dissertations defended in the meantime. Together, today we have gathered here in Pärnu and we welcome everyone. I see us as friendly folks coming together to introduce our research work results to each other, to make each other's acquaintances and to fully enjoy the social events. Also, it is no summer anymore. The seaside resort town Pärnu is both sightseeing in many ways. I hope you find time for exploring it too. I would like to wish us all plentiful days with memorable oral and dinner-up presentations, substantial discussions, lot of new knowledge and new cooperation ties. To sum up, our successful symposium, what is, as I yesterday told with my colleague, we started in 2000 years and it will be the 11th. Long tradition, and I am so happy to see you again here. And now, I think that our symposium will be very, very good in presentations and so on. I would like to ask, somebody, anyone have a word to say something about the Polymer Symposium? If no, then I declare the symposium open and let's start with work. Let's start with oral presentation session number 1. Chairman, Professor Andres Krumme, please, your turn.
Colleagues, I'm glad to welcome here also from my side, and I'm dishonored to lead this first session, and as time is already fast, so I'm also like to start it now soon. There is just one problem or question I have. Scientific committee have traditionally to select the best poster. So those posters are divided between 2 days, but anyway we should start the work quite soon. So if you can please, members of scientific committee, during the first coffee break we can get together there and decide how we will do this work or how we make the decision about the best poster. So, but let's start now, and we have the first plenary presentation. This is presented by Professor Elomaa, and presentation is called as Recent Trends in Polymer Science, a Nordic Review. Professor Elomaa, please.
Thank you, and good morning, ladies and gentlemen. So I'm a professor of polymer chemistry in the University of Technology at Tallinn now, and from the start of this year only. But I have been long time in Nordic Polymer Society, and that's why I will talk about Nordic research. I try to talk about what is going on in polymer chemistry in very general level and subjective, and also I can't cover all the things, but some pieces anyway. One source of my knowledge is Nordic Polymer Days, which is an occasion which is every year mostly in Helsinki, Stockholm, and Copenhagen. And sometimes it has been in some other towns as well, but the main players are shown here. And actually, I discussed this year one idea that because this conference is quite similar than yours, Baltic Polymer Days, so we will be having our 50th meeting soon, but you have 11. But anyway, it would be possible that Nordic Polymer Days will be arranged in Tallinn after 2 years. People who are organizing these conferences agreed, and I have an idea that we could discuss the possibility to join once these two small conferences, if people like to do that. Okay. About contents of this talk, I will talk a little bit about the background, what is going on, and then some new things which have emerged during 10 or 20 years actually. Mostly about polymer science, but also about the development of technology. If I put the lights okay, this can be seen anyway. But the background, there is a rapid development of new controlled radical polymerization methods, and then increasing amount of co-work with different other disciplines than polymer chemistry alone. And then behind all is, of course, this predicted depletion of oil and climate change, which require us to do things differently than before. This shows the possibilities. Everybody probably have noticed that top polymer chemists are doing all kinds of architectures of the molecules. Actually, a lot of, not very many new monomers have appeared. Instead, it's now possible to control much better those different architectures, part of which are shown here. Then what is also affecting the development is neighboring sciences. Physics give us a lot of new tools and there is a lot of collaboration with physicists. Also pharmacy and life sciences are very interested in polymers because they are using a lot of polymers themselves naturally. Also in molecular biology, polymers are more and more attractive. Actually they are dealing with polymers but don't consider those biologics. They are talking in a quite different way, talking about the sequences and all kind of biological effects of those molecules, but not so much how to be able to use polymers with macromolecules. Okay, this is a little exercise what are around us. I think chemistry and physics form the base, and then biology utilizes also chemistry and physics quite a lot. Technology is not possible without physics and chemistry, and also these biosciences pharmacy uses, among others, and material science uses a lot of chemistry, of course, and physics. And polymer chemistry, we are in the center in this map. And then there are a lot of projects around which are on the interfaces of these different disciplines, as you have probably noticed. There are new methods, there are new needs to develop. On the very academic meaning or field, and also in technical surroundings, these are valued. Contact searches are important. Then I must remind you about the fact that oil is consumed, half of it about, it is consumed now, and something must be done before any catastrophe, real catastrophe will happen. This figure shows that we are just at the peak of consuming oil, our fossil fuel. And this map shows where the rest of the oil is. So it's possible in Middle East to build towns like Abu Dhabi because there is the oil and they have enough money to do whatever they like. But on the other side, we can see that even here in Russia it's running out more rapidly. And also also in Europe and America is running out of oil more rapidly. And dependence of these resources will be more and more. There are prognosis how oil will be produced despite of this diminishing amount. This is so-called official forecast, and this is a speed where it was recalculated using the same data as on the left-hand side. So it's likely that energy sources are running out, and oil will be much more expensive in the future. Here is a figure of one researcher who did point out this situation some decades ago, Dr. Colin Campbell, who says laconically, as you see here, the story of oil is the same as a pint of beer, that it starts full but ends empty. However, the production is still increasing, at least this is a little old figure, but oil consumption tends to be increasing still, which means that the catastrophe is possible if nothing really happens rapidly now. And this shows how the synthetic polymer production is also growing all the time. This graphic is missed a little bit. It's over 250,000 mega, which is million tons. How to try to make situation better? There are many saving strategies. Of course, energy production from wind and sun side are very important. Then what is developed is fuel cell technology, which will save energy, and also the materials. Instead of oil, actually synthetic polymers don't use more than 5% of oil resources, so it's not a solution, but it helps. Also, renewable materials are used for material production, the polymers. Here is a figure of fuel cells. I participated to an Europe project where new membranes were developed for fuel cells, and the problem of car industry behind this project was that there is the polymer membrane between electrodes, and the system is such that hydrogen is burned, but so that temperature is low and product is electricity and not so much heat. Or this is more effective than this conventional auto. But the problem is also here that fuel cell is producing some heat, and when the temperature is very low, it's remarkable that the ratio of the need to cool the system is much higher than in conventional car, because the temperature difference is so much smaller. The problem is that modern fuel cells which are now in use, those hundreds of electric cars which are for demonstration purposes made, they must run at very low temperature. If the fuel cell temperature is going over this limit, it shows that more cooling is needed than in normal car. This axis is the required radiator front rear, and as can be seen that if it's a warm day, we experienced last summer many days it was near to 30 degrees. Then the cooling or the front of the car should be very large to cool the fuel cell of state-of-the-art technology. That problem was tried to solve, but I think it was not solved during this 3 years project called AVI. And what I tried to do, this is radiation source, a cyclotron which could produce protons so that we could make this kind of, in principle, this kind of etching of membranes. The idea was to put to the channels then conductive polymer and make this kind of films to the fuel cell. I must say that we didn't get enough conductivity to our membrane, but that was the idea. And then I have worked together with the Lund University. There are some structures made of, these are 4 fuel cells, proton conductive materials, basically phosphonate chemistry, because it was the trial that phosphonates don't need so much water and could run on higher temperatures than those conventional fuel cell membranes. And we did study carefully the morphology and self-assembly in those membranes which were produced, and quite good conductivity was reached, but it's still not a breakthrough in that technique. Also at the Nordic Polymer Days was presented many new molecular architectures for making sulfonated membranes, starting from this kind of very thermostable structure. Polysulfone is fixed and it can be decorated with various ways by sulfonated arms. This is Ilsted group and also this Patrick Janak was in this. Then one area which is important, of course, is this pharmacy and health sciences. One topic hot topic has been this chain delivery, in which different cationic polymers have been used for transforming DNA pieces to cells to produce new, for instance, therapeutic proteins, which are missing in some cases. There is the set of cationic polymers which can complex DNA, and these complexes can travel in the cells. Cells don't notice them, or don't find them hostile, but they don't take in any negative charge particles, but these are positive charge that can penetrate to the cell and even can be expressed those pairs of charge. Then one work we did I was in Kuopio in Department of Pharmaceutics, and we made encapsulated cells. The encapsulation method was biopolymer called alginate, and alginate cells after can be regulated by sulfur ions, and then these capsules are filled with living cells. The idea is to produce then therapeutical effects if those cells can secrete some therapeutic process for it. And this model did work quite nicely, but it was an exercise anyway. Model compound. Then, in nutshell, this Nordic polymer days, as you can see, there were 6 topics covering all the polymer chemistry, more or less. Quite little about plastics and technology, but more about synthesis and new structures. See some of these. For biomedical applications, there were this kind of compounds of architectures. For instance, these are just some examples. All 2-methoxyethyl acrylate is a chloride-compatible polymer, and they have reported new structures made of this polymer. Secondly, amphiphilic gum architectures on hydroxypropyl cellulose, and electroactive stars, superconductors, and throttling polymers for tissue engineering. This was typical biomedical application. This could have been in the synthesis part as well. Then nanocomposites were also very popular, and one of the core of nanoparticles was montmorillonite, a clay which can be suspended to very small particles, and which can then be decorated with polymers. And also nanocellulose was very, very popular. It has been for several years a hot topic. There are some examples. Polymer engineering and science. There was the talk of lactic acid stereocomplexes, and some papers about a new kind of flame retardant for polypropylene, and something like the bimodal method for electroactive polymer. Then, okay, polymer synthesis section, there are, I think, LP10 will later on Friday present the water-soluble system in detail. That was from heat group to water-detectable polymer so then on the technological link and polyethylene oxide together make a semiconductor that can be perhaps printed on paper. And, also many polymers made of controlled radical polymerization methods is produced. Then there was a section cellulose materials and materials from renewable resources, and they covered mostly methods for modification of cellulose surface. Cellulose in nano particle form or as a piece of paper. And then finally, polymer stability, polymer degradation, and long-term performance. There were a few pages of how electronic insulation is degrading under electrical heat, and also degradation of polylactic acid, which can be rather complicated because it can be made of different parts which are L or you probably know that it's the stereochemistry of polylactic acid is such that you can have at least two forms, and they complex to make different, more stable crystals, and degradation of such complexes was also studied. So we find that these keywords are now topical bio and nano, and this molecular architecture. Methods are a lot of work has been done with controlled polymerization, radical polymerization, AVI and draft methods are very common. Also, click chemistry helps to make those interesting new structures. And ionic liquids, they were not so much this time. Maybe they are also coming more popular. But these are new ideas which are coming popular as biomimetic and supramolecular structures, and studies of self-assembly means that it's possible by these new methods to make species which can then, or large molecules which can act a little bit like proteins, and they find some superstructure because they are attracting something. Okay, why biopolymers are so popular? We have these obvious reasons. I don't read them again to save time. I will show a small research of how much these keywords are in use. Nano is important, of course, but it wasn't very popular, at least it's 20 years ago. I will show how this has been developed. But of course, it's very attractive to do things in nanoscale. But that's what the polymer chemists have been doing all the time. But now we have new tools to inspect those products. you can even see single polymer molecules by new methods. So I did this kind of exercise about bio and nano. I selected these words, biopolymer and nanoparticle, and checked how they have been occurring in publications. This shows from 90s, they were, nano started to be popular and bio was growing more steadily, and it will continue to today's situation. Nano has reached its popularity top, perhaps, and bio is increasing, is still increasingly popular in this biopolymers, especially, and nanoparticles. And then if we look more closely to the scanning probe microscope or microscopy was the keyword, then we see that, people are already tired, a little tired to scanning probe microscopy, but it's still very, very popular and start to be aware of it. But then if we combine bio and nano, which is typical in all applications nowadays, we see that it's still going strong, and this combination. So nanocellulose was the key word, which is becoming still more popular. What is nanocellulose then? It's quite new word. You don't necessarily find it from a dictionary, but it can be many kinds of small pieces of cellulose, as seen in this table. The size is from few nanometers to something like the length here can be 500 nanometers. Here, and the width is usually somewhere around 10 or less. And how do they look like? They are lots of small needles, not very exciting looking. We know that the crystalline cellulose is very difficult to handle, or it doesn't dissolve, and if you try to melt it, it will be destroyed. But a lot of chemistry is now done on these small particles. In Finland, the forest industry's research was reorganized using, there is a new company called Forest Cluster, which is organizing research. The idea is to get more value of wood, and that by doing all kinds of things, biofuels, textiles, plastic as well, to utilize more effectively all the parts of wood. And that's why also this nanocellulose is now giving much value. What I have been involved to is to make lactic acid resins, thermosex from lactic acid. There are on market already lactic acid plastics that thermoforming, but this with Professor Jukka Seppälä and his company, we have developed this resin which can be considered as biopolymers to very high extent, and here is so the thermosetting composites are very strong. And here are examples of structures. One is with cellulose, with polylactic acid resin, and this is with plastic. It's possible to make pieces which are nitrous bio-based. So, in more generally, about bioplastics, I refer to a presentation from the beginning of this year by Mikael Karus from Nova Institute. He reported that these biopolymers are really coming. This is a new technology, maybe, but old feedstock. And here is estimating how this will grow, and this is quite amazing to what we know about industry on this field. So the bio content of this material, biocomposites, will increase, and the amount will increase a lot during the next 10 years. But we should remember that this is only 1% compared to conventional plastic. To summarize a little bit, the frontals are in complicated tailored structures for nanoscale devices and all kind of more or less clever polymers can be also produced which have different functions. Usually they can be on or off the swell or not swell, something like that. But also the biomimetic materials will probably be developed further. To end this presentation, I summarize today's challenges in developing sustainable, renewable materials and technology for the time after seed oil, which we are living rather soon. And polymer science has an important role in that. And polymer science has a big role also in biomedical and most fields of nanotechnology. Thank you for your attention.